Hello, good morning, everybody, to those who are watching me in Tehran. Firstly, I would like to thank the organizers of our test 2020 to give me this opportunity to present my work in mixed criticality scheduling to all of you. It is a bit unfortunate that I'm unable to attend in person. I would have loved to visit Tehran. It would have been my first visit actually to Iran. Uh, but nevertheless, given the current pandemic situation, I guess this is the next best option that we have. I hope that I can convey the message with as much rigor as I would have liked to convey if I was in person. And hopefully the virtual setting still keeps the spirit of the presentation and the content and passes the message on to you. So the topic of my talk is efficiently safe, decoding the dichotomy in mixed criticality systems. As you can see, it is a very interesting topic in the sense that we are dealing with critical systems, safety critical systems, automotive, avionics, industrial controls, and so on, where safety is very fundamental. But recently, over the last decade or so, there has been this big push to make them also efficient. So safety should not come at the cost of efficiency. And the main focus of mixed criticality studies have been how to combine safety with efficiency. So I'm an associate professor at the School of Computer Science and Engineering in NTU, Singapore. And the work I'm going to present today is collaborative work, joint work with several collaborators distributed globally, including some of my students. Some of those collaborators are listed on this slide. So the overall structure of the presentation is as shown here. So I'll first give you some motivation for mixed criticality scheduling, kind of justify the need for this kind of scheduling models, give you some background, both in real time in general and mixed criticality in particular, and then focus on three specific techniques that we have developed in NTU together with our collaborators. One of them will focus on multiprocessor scheduling. So essentially how mixed criticality systems can be efficiently deployed on processing systems with multiple cores. And then the last two studies will focus on single or uniprocessor systems, essentially processing systems with one core. And I will talk about more recent work in the area of mixed criticality, where we focus on how to get efficiency in terms of providing support for some of the less critical applications in such a paradigm. So broadly speaking, what are real-time systems? What are cyber-physical real-time systems? So these are traditional embedded systems, cyber-physical systems, but with stringent timing requirements. So correctness for us not only depends on the functionality of the system, but also on the timeliness, on whether the results are produced at the correct time. Several domains, as I said previously, avionics, automotive, manufacturing, etc. Two key trends kind of define this domain as of today. So one of them is this rise in computational demand for software, because several applications are getting deployed. The systems are evolving from mechanic-centric to electronic-centric, which means there is a big surge in demand for different types of applications, mainly driven through this trend. Orthogonally, from the chip vendor's perspective, from the hardware perspective, there is a different trend, which is that they want to shrink. They want to shrink the size of the hardware. This is because of swap constraints and also the physical constraints of deploying hardware on cyber-physical systems. So there is a trend towards integration. So naturally, these two combined then lead to this scenario where several applications, maybe of different importance, doing different functionality, are co-hosted on the same physical hardware, let's say on a multiprocessor or even on a uniprocessor. So that gives rise to mixed criticality real-time systems. So these are essentially real-time systems, systems with timeliness requirements, having different levels of notions of criticality or importance, and co-hosted on a single processor. It could be a multiprocessor with many cores, or it could be a single processor with just one core. Interesting to note is that mixed criticality systems are not new. they've been around for at least 2 decades, to my knowledge, and even more. So one of the first or earliest practical deployments of mixed criticality systems is in avionics, classically known as integrated modular avionics, where several different applications in avionics were co-hosted on the same physical hardware. I think the earliest airplane model that I'm aware of which used this integrated modular avionics is the Boeing 777, probably dating back to the late 80s or 90s. One thing fundamental about how these mixed criticality systems have been deployed so far is that resources are statically partitioned between the applications because they're very critical applications. You want to make sure that you provide sufficient resources to each one of them. So they are statically partitioned. So offline, you make some analysis and you make some decisions on how the resource, the physical hardware, should be distributed among these applications. This ensures safety because you kind of provide isolation, fault isolation, some guarantees on availability of resource and so on, but it is not very efficient in terms of resource utilization. Because essentially, when you provide such guarantees, static partitioning guarantees, you need to ensure that you have reserved sufficient resources for the worst case scenario. But the worst case scenario may not happen often, which means most of the reservations that you are doing are not often used by the applications. So this leads to underutilization of the resource. And consequently, we then need to figure out how to deal with this dichotomy of safety versus efficiency. So that brought into focus this notion of mixed criticality task model or mixed criticality systems in general. Ironically, it was introduced by Steve Weston, who was a scientist in Honeywell Aerospace in those days when he presented this paper in RTSS 2007. And the idea he proposed was very simple. So he said, instead of static partitioning, why don't we do dynamic partitioning of the applications based on multiple execution budgets for the tasks or the applications? So essentially, you have some smaller allocation of resource or budget, in this case, execution time, for the normal scenario. And essentially, you make sure that all applications are able to meet their deadlines based on this normal. In those rare cases, in those worst case cases where they require additional resources, more budget, you allow conservative larger budgets to be given to certain applications, certain critical applications. However, this implies that during those rare periods of time, there are other applications in the system which will not be able to get sufficient amount of resources, and consequently, maybe there are a few deadline misses. But this is okay because critical applications which really require those resources are then guaranteed to get those resources when they need them. So this is the broad idea of mixed criticality systems that was introduced. So the key challenge when we look at mixed criticality systems is how to efficiently allocate processors to such systems, to such applications, while satisfying these kind of dynamic requirements, partitioning requirements. So we'll focus in this talk on both uniprocessors as well as multiprocessors. I will first focus on multiprocessors and then move on to uniprocessors. But before I present the solution techniques, I will spend a little bit of time giving you a little bit of background on the kind of task models, the notations that we use in the rest of the talk. I guess this is very important, particularly if you're not from the real-time scheduling community, to be able to get a grasp on the techniques that we are discussing here. So in real-time systems or real-time scheduling in particular, one of the fundamental units of workload is called the real-time task model. So essentially it defines a unit of work, typically repetitive in nature. So each instance of the work is called a job in common terminology. And it is defined like a task y in this case, as shown in this slide, is defined using 3 parameters, Ti, Ci, and Di. Ti denotes the minimum separation between successive instances and their release time, or in some other cases, it could just define the exact separation between the release times, in which case it is called a period. So it is essentially how often the workload shows up in the system. Ci denotes the worst case execution time estimate for this workload. So essentially it's a metric, it's a measure of how much computation time it will take, every instance of this task will take when it is released in the system. And Di is relative deadline, which is from the time it is released until when should this task be able to complete? So whatever its requirement is, whatever its execution time requirement is, your scheduling policy, your framework should ensure that this much amount of resource is processing capacity is made available to this instance of the task within this interval of time. So as you can see in this figure, the blue arrows show the release times of the instances of the task, and the red arrow shows the relative deadline. So every instance must receive sufficient resource allocation within the window, basically encompassing the blue line and the red line, so that you are able to meet its requirements. So a classical real-time scheduling problem then boils down to this: how to schedule a collection of such tasks. It could be 2 or more on a processor. It could be single core or multi-core. And then the notion of schedulability comes in, which is essentially saying that a system like this, a task system like tau, is schedulable by some scheduling algorithm if all instances, all job deadlines are met under every feasible job release pattern. It is important to note that the job release patterns are not fixed, especially if we look at this notion of minimum release separation time. So there is some variability in how instances could show up, and the scheduling algorithm should ensure that the task system is schedulable irrespective of this release pattern. So once we understand what a real-time task system is, then the classical issues of how to allocate resources to these task instances come in. And this is where real-time scheduling comes into the picture. So a scheduling algorithm is essentially a strategy, an approach to allocate processing capacity to the various task instances, the jobs, or in a way determine the order of execution of these jobs. So the most well-known, I guess some of you are at least familiar with this, is the earliest deadline first scheduling algorithm. Put it very simply, it says among all the jobs that are currently waiting in the system, to allocate the processor to the job which has the earliest deadline. Of course, given a scheduling algorithm, you want to know whether this scheduling algorithm can successfully schedule a given task system, the notion of schedulability. So tests exist. These are mathematical formulations which can be used to determine whether a given collection of tasks can be successfully scheduled, meeting all deadlines by this scheduling algorithm. Tests can be either sufficient in that if you are successful, if the test is successful, then you know that the system is meets all deadlines, and it can also be sometimes necessary, in which case they become exact. An example of a very simple fundamental test for earliest deadline for scheduling is shown on this slide, which is for implicit deadline task systems, where Ti equal to Di, the parameters. And essentially it says that the overall utilization of the task system should be no more than 1 for a single uniprocessor system. So this is a very classic result in real-time systems. So let's focus on this parameter Ci, which is essentially the worst case execution time of a task. Now, as you can imagine, probably some of you already work in this domain. Precisely computing this parameter is a very hard problem. It's very difficult, if not impossible. So it depends on a lot of factors: hardware states, inputs, control flow, and so on. Success has been achieved in limited form under several assumptions, but in general, it is very hard to generalize and compute these parameters precisely. Moreover, even if you're able to use some techniques to estimate these parameters, typically you tend to come up with conservative upper bounds because you need to make sure that whatever estimates you come up with, it is safe from the perspective that if you allocate resources based on this estimate, then you will never miss deadlines. So as a consequence, you tend to come up with conservative upper bounds, and naturally, the more critical a task is, the more conservative this bound tends to be. So this is what is shown in this figure here, which is from a very, very classical paper in worst case execution time techniques by Reinhard Willem and a bunch of others. And what this figure essentially shows is that the true execution time profile, which is given by the histogram plot here, would be somewhere as shown. Whereas if you just do measurements and you just observe the execution times, maybe you don't really observe all the values, and therefore you end up with a kind of optimistic estimate here, as shown here and here. But if you then do some analytical techniques, maybe some static analysis or some other approaches which are more rigorous and have some guarantees, then you probably end up with pessimistic bounds, which are conservative in nature, and primarily because of some of the assumptions that you need to make and to ensure that the bound is correct and time. So in general, WCT is a hard problem. There is a lot of pessimism. So that motivated the need for this mixed criticality task model, essentially saying that why should I use these conservative upper bounds to allocate resources all the time? Why not allow some flexibility and then use the dynamic partitioning framework to allocate resources dynamically when there is a need in some rare worst case scenarios? So a classical dual criticality mixed criticality task model is shown in this slide. And it's a simple extension of the classical real-time task model. So you have the period or the minimum separation, you have the relative deadline DI, and you have this new parameter, which is essentially the criticality level of the task. So here, because it's a dual criticality task model, there are only two criticality levels, LC and HC. LC stands for low critical and HC stands for high critical tasks. Okay? So less critical and more critical. So there are two different types of tasks from a criticality perspective. And then CI is your execution time estimates, but now there are more than one potentially. So for example, in this case, we could have two estimates for the execution time of a task. For the low criticality task, we just have one estimate. They are both equal in value. This could be just the upper bound, the conservative upper bound, or it could be derived from some other mechanism. For the critical task, for the high critical task, we have two distinct estimates. One strictly lower most of the times than the other. One of them could be obtained maybe by measurement-based techniques. So they are optimistic. They are not always guaranteed to bound the execution time, but maybe for 95% of the cases or 99% of the executions, that amount of resource is enough. And then there is a conservative upper bound, which is assumed to be an upper bound of the actual worst case execution time, so that that bound will never be violated. So in this task system, then you can split the system into two sets of tasks, essentially the high criticality task denoted by tau h, and the low criticality tasks, which is the remaining tasks in the system. So in this kind of a mixed criticality model, the system behavior can be split into two modes, low criticality mode and a high criticality mode, or LC mode and HC mode. And the mechanism functions like this. So the system starts in the low criticality mode, LC mode, and everybody is executing normally as long as no HC task, no high criticality task executes beyond CIL. So the estimate, the lower estimate of its execution time. So as long as no critical task executes beyond this CIL, everybody is executing normally, and this is essentially a classical real-time system where all deadlines must be satisfied. But once a single HC task executes beyond CIL, it requires more resource. Then the system will switch to HC mode. So it makes a mode switch. And some properties change, some requirements change as we switch mode. So what are these requirements? We'll look at in the next slide. So the notion of schedulability now has been slightly adapted to deal with these two modes of operations in the system. So a task system is said to be MC schedulable by a scheduling algorithm if in the low mode, in the LC mode, it's the traditional real-time systems guarantee, which is that every job is completing its budget, which is equal to the lower estimate of the budget by its deadline. So all jobs have to meet deadlines. But once a mode switch occurs, then essentially the requirement on the deadline satisfaction is now shifted to a subset of the jobs, tasks. So essentially all the jobs which are high critical jobs or high critical tasks. So what we need to make sure in the HC mode is then that only the high critical jobs are able to meet their extended budget, the bigger estimate of budget, by their deadlines in the HC mode. And this requirement, important to know, is also true for a job, for a HC job, which was released before the mode switch, but did not complete by the mode switch. So it is kind of a carryover job, which continues to execute even after the mode switch. So even such jobs, which are carryover jobs, must meet their deadlines with this additional budget that they require. Okay, so this is the adaptation of the classical schedulability requirements from real-time system to mixed criticality real-time systems. So given this framework, two fundamental challenges. So one is, it has been shown that scheduling is hard. So MC scheduling is a hard problem, NP hard problem. I think there is a reduction from 3 partition, if I'm not mistaken. So we need good approximation algorithms. How to ensure theoretically good performance, as well as in practice, a large collection of task systems are able to meet the requirements. The second aspect is this notion of criticality versus importance. So is it really true that a job or a task that is low critical or less critical is not important? Can I treat it as background requirements? Probably not the case, and certainly not the case if you look at real applications from the real world. So then we need to also provide some guarantees for the low critical jobs. It cannot happen that mode switches occur very often in the system and the low criticality jobs are just ignored, their deadlines are never satisfied. So this will not be acceptable from a practical viewpoint, and this has been a big hurdle in terms of how industry looks at mixed criticality scheduling. So it's an important problem to look at as well. So we will look at both these problems in the subsequent slides. For multiprocess scheduling, I will focus on the first problem here, which is developing good algorithms, approximation algorithms with performance guarantees. And for the uniprocessor framework, I will focus on the second problem, how to provide guarantees to the low criticality jobs. So that brings us to the first solution technique that we have developed. This is on multiprocessor mixed criticality scheduling. So what is the problem? So we are given a dual criticality MC task system, a mixed criticality task system. So the task system that I presented earlier, and it is scheduled on a multiprocessor platform comprising hem homogeneous cores. So all the cores are identical. It doesn't matter where the tasks run, the requirements are similar. We will focus on a specific type of scheduling algorithm in multiprocessor called global multiprocessor scheduling. So what is the idea of global multiprocessor scheduling is that at runtime, tasks can freely migrate from one core to the other. So an instance of a task could be running on one core, you could preempt it and migrate it to another core, and it will continue running on the other core as if nothing happened. So this is a kind of global scheduling where there is complete freedom to the tasks in terms of how they migrate. As you can imagine from a theoretical perspective, this has some flexible, because of the flexibility offered in the scheduling paradigm, there are some very strong theoretical results that one could obtain. Of course, practically speaking, maybe there are some limitations because when you migrate, it doesn't come for free. There are migration costs that need to be considered and so on. So one of the things in mixed criticality is what we assume is that under global scheduling, when a high criticality task on a core triggers a mode switch, so it executes up to this lower estimate of the budget, unable to finish its requirements, so needs more resource, it will trigger a mode switch. But this mode switch would be immediately reflected on all the cores. So it is not a mode switch specific to a core, but a mode switch across all the cores. This is reasonable because we are essentially dealing with global scheduling. So the other aspect is that once this happens, we assume, remember, in the high criticality mode, we only need to satisfy deadline requirements for the high criticality tasks. So what we assume very conservatively, and I will come back to how this can be relaxed later on. But very conservatively, we assume that all the low criticality tasks on all the cores are immediately suspended thereafter. So we don't need to meet their deadlines anymore. Okay? The other assumptions that I make in this work are we focus only on implicit deadline tasks, so Ti equal to Di for all the tasks, as well as we ignore any overheads in terms of migration overheads and preemption overheads. So we need to design a global multiprocessor MC scheduling algorithm, which has good performance, meaning if you give me a task system that is feasible by some algorithm on multiprocessor, then it should be feasible by the algorithm that I'm trying to develop, ideally. So good performance, a large class of task systems should be schedulable. And I want good theoretical performance, bounded performance. So one way to achieve this theoretical bounded performance is this notion of speed up bound. So what is speed up bound? So speed up bound of an algorithm is the minimum value by which the processor speed on every core must be increased so that every feasible task system now becomes schedulable under your algorithm. So given an algorithm, I want to increase the speed on every processing core by a certain factor such that any feasible task system in the original platform is now schedulable under your algorithm in the new faster platform. Okay, so that's a theoretical measure of how good your algorithm is. So lower the speed of bound, smaller is the factor by which you have to increase the speed of the processing core, better is your algorithm. And if you can also show that you cannot go any lower than this, then you also achieve optimal algorithm from a speed up bound perspective. From a speed up perspective, you get optimality. Note that it is an NP-hard problem, so we don't expect to achieve zero speed up in terms of performance of the optimal algorithm. So we don't expect that any algorithm would be able to achieve the performance of an optimal algorithm with no speed up. Okay. Okay, so that brings us to our approach. So we're going to focus on this concept of a fluid execution rate-based mixed criticality schedule. So what is a fluid execution model? So under the fluid execution model, we relax how a task executes on a processor. A task can execute using fractional execution rates on a hypothetical processor. So it's a very theoretical concept. So as you can see in this figure, this task is executing with only partial use of the processor. So there is a certain capacity which is unused. This allows multiple tasks to make progress at the same time, even on a single core. This allows us to achieve very strong results, theoretically speaking, on schedulability. Of course, from a practicality perspective, you cannot implement such algorithms because you cannot execute multiple tasks on the same core at the same time. So you need to translate these fluid schedules into non-fluid forms. Several techniques exist and they are applicable in the non-mixed criticality setting and could be adopted for the mixed criticality setting as well. So in the non-mixed criticality setting, this is how the fluid scheduling framework worked. So for every task, you try to find a certain rate, theta I. Okay, this rate is less than or equal to 1. So this is the rate at which the task is executed. So you want to allocate rates to each task in the system such that these two conditions are satisfied, task schedulability and platform feasibility. So platform feasibility essentially just says the total allocated rate to all the tasks combined should not be more than the number of processors, processing cores available on your platform. This is reasonable. You cannot execute more than what is available from a resource perspective. The schedulability of the task says that as long as the rate for a particular task is such that it can complete its execution requirement, worst case execution requirement, this is non-MC, remember, by its deadline Ti, then it will meet its deadline. So this is a very simple schedulability test. So as long as you can come up with an algorithm to allocate these rates such that these two conditions are satisfied, you get a fluid scheduling algorithm which can meet all the requirements for schedulability. So how does this look in the mixed criticality setting, in particular for dual criticality, where tasks have two rates? Well, it's simple. You can say that each task will be allocated two rates, a low mode rate and a high mode rate. So whenever there is a mode switch, you change the rate. So you execute at a lower rate, theta IL, before mode switch. But when mode switch occurs, because now your requirement has increased, your budget allocation has increased, you probably have to execute at a faster rate than before to meet the requirements or to meet your deadline. So you try to increase your execution rate. So essentially, you now have each task, especially the high criticality task, which can now execute at two rates, one in low criticality mode, another in high criticality mode. The low criticality task just continues to execute with one rate in the low criticality mode. And after the mode switch, based on our assumption, this low criticality task will just be suspended and will not execute at all. So the problem then becomes how to find these two rates and how to allocate the rates for the tasks in a dual criticality setting. So from a schedulability perspective, conditions are very similar, as you can see. So platform feasibility just says in each mode, low criticality mode, the total allocated rate should not be more than the platform requirements, the platform capability, and same for the high criticality. From a schedulability perspective, if the jobs are in pure low criticality mode, just make sure that the low rate allocated to the task is no more than its budget requirement. In the pure high criticality mode, if an instance of a task is only executing in the high criticality mode, you make sure that the allocated rate again is sufficient to meet its new worst case budget. But there are some carryover jobs. These are jobs which basically start in the low criticality mode and then continue to execute in the high criticality mode across the mode switch. So these jobs have a special condition, which is essentially making sure that you get a certain amount of budget, which is CIL. You now require an additional budget, which is then up to CIH. So the new budget that you need is CIH minus CIL. So CIL amount of budget you get using the lower rate theta IL. So the time it takes to get the CIL budget is essentially CIL over theta IL. And if I subtract that from TI, I get the amount of time remaining when a mode switch occurs in the worst case, by which I should be able to get CIH. So that gives me a certain amount of rate that is needed to execute in the high criticality mode, such that I can satisfy the requirement of even carryover jobs. So once you have these schedulability conditions, we developed algorithms to compute these rates, how to allocate rates. So given a collection of tasks, given these conditions, how to determine rates efficiently. So we came up with several rate assignment algorithms over several papers and in fact spanning several years. And essentially what we have, a summary of those results are in this one slide. So we have optimal rate assignment algorithms for this model. Optimal in the sense that if there exists some allocation of rates such that the task system becomes schedulable under the dual rate fluid model, then our algorithm will find these rates. This algorithm is essentially a convex optimization based technique. We use the idea of water filling or bucket filling technique from Stephen Boyd's book, and it results in a quadratic runtime complexity. Certain simple improvements to this algorithm have also been made based on some sorting techniques, which reduces the complexity further to log linear. Additionally, orthogonally, actually, with collaborators from Washington University and Florida, we also shown that there exists another rate assignment algorithm, which is not optimal from the perspective of the assignment of the rates per se, which is called this MCF, Mixed Criticality Fluid Rate Assignment. However, it is linear time, so much faster to assign rates than the previous one, but it has optimal speedup bound of 4/3. So essentially, this speedup bound, first, it applies to the previous algorithm as well, the OEARA algorithm as well. And the speedup bound has been shown to be optimal in the sense that there cannot exist any other multiprocess scheduling algorithm which can have a speedup bound smaller than 4/3. So this closes a very important problem in multiprocess scheduling. So what we have essentially shown through our work is that we have come up with a global scheduling algorithm which can optimally, from a speedup bound perspective, schedule dual criticality, mixed criticality task systems. And we have also developed polynomial time algorithms to allocate the fluid execution rates for these task sets in order to achieve this optimal speed up. So that's kind of the summary of the results in the multiprocess setting. So moving on to the two topics on uniprocess scheduling, I'm going to shift gears, not worry so much about the scheduling algorithm per se, and now start worrying about how to provide guarantees to the execution of the low criticality tasks or the less critical tasks. How do I get some assurance that these tasks will be able to meet their requirements, mode switches don't occur often, so on and so forth. So looking at this work, so looking at the classic MC task model, the model that we have been looking at so far, there are a couple of things that come out, a couple of shortcomings that come out. So one of the first thing is when a mode switch occurs, all the low criticality jobs are suspended, as you saw in the case of the multiprocessor setting. And this is done under the assumption that all the high criticality tasks will immediately require this additional budget of CRH. So all the high criticality tasks suddenly require this extra budget, and all the low criticality jobs are suspended to serve this additional demand. This seems like a very restrictive assumption. It may not hold in practice in general. The other aspect is if you look at this low criticality budget CIL for the high criticality tasks, they are not really execution time restriction on the high criticality task or anything like that. They're essentially just a designer specified parameter which controls the mode switch in the system. the lower the CIL values for the high criticality tasks, more often you're going to see mode switches in the system, which means more often the low criticality tasks are essentially going to get some degradation or they're going to be suspended from execution. However, higher the values of these CIL budgets, less often the mode switches will occur. Well, in the limit, if you make CIL equal to CIH, you get the traditional real-time task model, which has no notion of criticality. But as we saw earlier, this kind of a restrictive task model has limitations in terms of its ability to utilize the resource efficiently. So then the natural question is, how does somebody pick these CIL values? How do you trade off the frequency of mode switches with the kind of support you provide to the low criticality tasks? So that's what we want to address. Can we change this model in some way? Can we come up with a new model which still deals with the notion of criticality as understood in the literature so far, but is able to provide some guarantees for the low criticality tasks? So that motivated us to propose this model called the dynamic mixed criticality task model. We call it dynamic because compared to the existing mixed criticality model, the previous model, where all the parameters were statically specified, you will see in this model that things are more dynamic. So decisions are made at runtime on how to distribute available resources among the various tasks in the low mode as well. So the dynamic model essentially goes back to the traditional real-time task system and says, I'm only going to use a single estimate for each task in terms of the worst case execution time estimate. So this is the CI, parameter CI. So every low criticality task has one value CI. This is same as the mixed criticality task model. The high criticality task also has only one estimate, and this estimate is the conservative upper bound, the CIH. CIL is unspecified. So we leave the burden out of the designer. We take the burden away from the designer, and we now incorporate mechanisms in our framework, in our scheduling framework, to come up with estimates for the CIL based on how tasks are executing or how instances are executing to provide some efficiency in terms of reducing the frequency of mode switches and so on. So what we then do, given this very simple task model, is we come up with an offline, so this is an offline computation, we come up with a system-wide low criticality budget, okay, which is a fraction of the total budget allocated to this task, to the high criticality task. So the total demand of the high criticality task, a fraction of that is used as a low criticality budget for all the high criticality tasks combined. So this is not budget for each task, but this is budget for all of them combined. And then additionally, to provide some guarantees to the low criticality tasks, we also allow low criticality tasks to continue executing after mode switch. So this is the standard extensions to mixed criticality model that have already been developed. So there is nothing fundamentally new in this aspect of the proposal that we are making. So how does these two work? How do beta star and alpha work? If you think about it, a larger beta star implies that mode switch is less likely because you're reserving a lot of budget in the low criticality mode for the high criticality tasks, which means that the low criticality task can receive full budget for a longer duration of time because mode switches don't occur. However, this also means that once mode switch occurs, the low criticality task probably cannot get much budget in the high criticality mode. Conversely, smaller the beta star, there may be frequent mode switches, but if such frequent mode switches occur, the low criticality task may continue to receive a substantial amount of budget even after. So it's a trade-off, and there are several ways to explore this trade-off. I'm not going to go into the details of that. So one of the fundamental questions that comes up in this task model is how do you distribute this collective budget that we have computed in the low criticality mode for the high criticality tasks collectively? How do we distribute it among the individual tasks while ensuring that all deadlines are met? So this is the fundamental question that we need to answer. So here we use a very simple parameter. We monitor the execution of jobs of the high criticality tasks, and we record the largest observed execution time of any job in the past, let's say from an ideal instant or from in the latest busy period, for example. So once we have this, we have a strategy which is called maximum execution based allocation strategy. The strategy is again very intuitive. So it says, I have a total budget that I want to allocate to all the tasks, high criticality tasks in low criticality mode. I will reserve budgets to individual tasks based on their observed maximum execution time in the past. And once this reservation is done, whatever is remaining, I will allocate to the current task that is going to execute in the system. So I keep updating these budgets that are allocated to the different tasks, high criticality tasks and low criticality. And these budget updations are based on the observations in terms of the maximum observed execution time in the past in the current busy period, let's say since the last item. And once I start executing a job with this reserve budget, if I see that the budget is not enough, I will trigger a mode switch. Interesting results that come out from this very simple technique is the following. One, this very simple strategy is optimal in terms of delaying mode switch compared to all static allocation techniques for CIL. So no matter how you allocate these CIL values offline to the various tasks, the approach we have is going to do better in terms of delaying the mode switch. So the number of mode switches are going to go down compared to all of these other techniques that you could come up with where you statically reserve CIL values for the various high criticality tasks. The other aspect is that we also have done some extensions to this strategy where we can use some slack. So because we are using this maximum observed execution time, so as you can imagine, over time, this value keeps building up, it keeps increasing in a particular busy period. Of course, we can reset it once an idle incident occurs, but until then, this value keeps building up. So one way to deal with this inefficiency of the paradigm is that we can use the slack. So whatever slack we monitor in the system, we first use that slack before we consume our own budget. So this delays the mode switches for. So this is the other technique that we came up with. Of course, there are some experimental results in the paper, which I'm not going to go into in the slide now. So this brings us to the last topic of the presentation, which is mixed criticality from a very practical perspective. So we wanted to look at automotive systems and ask the question, what are the issues when we want to take mixed criticality scheduling and the mixed criticality framework to automotive systems, and how we are going to deal with those issues. And some very interesting observations have come out, and I would like to present that here. So when we look at mixed criticality for automotive systems, there are several issues that come to the fore. So one of the first questions that come up is that this notion of criticality in automotive, it is basically an abstraction of several factors. In particular, there are at least 3 different factors that decide the criticality of an application or a task in automotive. So in automotive, they have this term called automotive safety integrity level, which is essentially obtained from ISO 26262. It's a standard specification where automotive industry or automotive vendors are encouraged to use this specification to decide on the criticality levels of the various applications. So it essentially describes the risk reduction that is required for various applications, depending on the safety functionality that is being implemented by that application. There are 4 levels, A to D, D being the most critical and A being the least critical. And there are 3 factors that affect, determine this level. So severity of an hazard, the controllability of the vehicle when that hazard materializes, and the probability of exposure. How likely is this hazard going to occur? So as you can see, the notion of criticality is very nuanced. It's not very straightforward. Consequence of this is that criticality may not be synonymous with importance, which is very fundamental in all many of the existing mixed criticality task models, particularly those that I've spoken about earlier in the talk. So this notion that a critical task is more important than a less critical task is may be flawed in this setting. So I'll give you some examples. Consider a simple example where you have cruise control, adaptive cruise control. So you're kind of judging your distance to the lead vehicle and trying to control the speed of your vehicle. And a hill assist application. So hill assist is trying to provide you some additional traction when the car is going up. Clearly, hill assist is a less critical task than cruise control. But does that mean it is really less important? What if the vehicle is actually on a hill? Then probably the hill assist task is very important in that particular setting, and it is not okay to just suspend it because of some budget requirements. So lower ISIL applications can also be very important. That's one conclusion you can draw. Another important aspect is this notion of ASIL decomposition, which is specified in ISO 26262. So the idea of ASIL decomposition is you want to satisfy some very important safety requirements, very high ASIL safety requirements. One approach to satisfying that requirement is to decompose it into independent mechanisms, which are certified to lower ASIL levels. So they are apparently less critical, right? Because they are certified to lower ASIL levels, but they are both independent approaches and they collectively provide you this higher ASIL guarantee on the safety. So here again, the two ASIL requirements here for the radar and the V2B, although they appear to be less critical from the ASIL perspective, but they collectively provide you a very important safety requirement, which is high critical safety requirement. So it is not okay to treat them as low criticality tasks and just suspend them whenever budget requirements demand that we do so. So this is another aspect that comes up. The third issue is that somehow this notion of who can overrun budgets. So budgets are allocated. There is a normal mode of operation. Some tasks require extra budget. When they require that extra budget, you do a mode switch and you allocate some extra budget and then you penalize some of the other tasks. Who can overrun this budget? This seems very restrictive in the current models that we have seen so far. And I would like to argue that this may also be not reasonable in practice. So again, if you go back to the hill assist application, if you're on a hill, is it not unreasonable to say that hill assist should never require extra budget than what you had allocated it in the static analysis technique? I mean, that seems a bit unreasonable, I think. So it should be reasonable to allocate extra budgets to whichever task that needs it, depending on maybe the context in which it is operating. Another way to think about this, another example is adaptive cruise control, for instance, could have different aspects to its functionality. So there could be a safety functionality that you need to maintain a certain distance with the lead vehicle. But there could be a performance aspect to it, like how smooth is your control? So when you accelerate or brake, are you making sure that you're not giving too many jerks to the passengers? So it is possible potentially, although this is a very important and critical application, that you may degrade some aspects of cruise control without affecting safety, like you can degrade performance, for instance. So combining all these, essentially we decided to come up with a new mixed criticality task model, which is inspired from the automotive domain. And one of the aspects that we wanted to incorporate in addition to these challenges was this notion of multiple degradations allowed for a task. So essentially what it means is you can have highly critical tasks or which could be degraded. You could have low critical tasks which could overrun budgets. Everything is context dependent, the operating modes, who is overrunning at what point in time, and so on. And further, what you degrade to could also be multiple choices. It doesn't have to be a single budget that you degrade to. Right? So degrade here means that you reduce the budget, for instance, that you allocate to the task. So an example would be a LiDAR task. So a LiDAR processing task, you could configure the LiDAR using several factors like scanning frequency, acquisition angle, and so on. You get certain budgets, certain computation requirements, and different modes of operation. So normal mode and several degraded modes. So in summary, a low critical task does not always perform a low critical function. It may be important. Degradation should be possible for any task. Multiple ways of degradation should be possible for tasks. And further, degradation could be context dependent. Okay? So the objective is to combine all this and propose a new modeling framework. And that's what we came up with. So we basically decided to come up with this context-aware mixed criticality task model, where essentially what we are saying is that for every task, there is the traditional period or the execution time, the minimum separation time for the task. There is its criticality level. Let's say it is one of many criticality levels potentially. Right? In terms of budgets now, we provide a vector in the task model. So it's a set of potential budgets that this task could have. And the budget that is allocated to the task depends on what are the other tasks in the system doing. So whether they are executing in their normal mode, whether they have exceeded their budget and they've overrun their budget and therefore now they're executing in their safe mode, or whether there is some degradation that needs to be done. So essentially, each task has a normal budget, which is just the budget that it will start with. It will have a safe budget, which is the budget that is essentially a larger value, a conservative upper bound of the worst case execution time. Think about it that way, which gets allocated to this task whenever it overruns its normal budget. Additionally, it has a vector which defines what its behavior should be when some of the other tasks in the system overrun their budgets. So this is what we call context-aware mixed criticality task model. So essentially, the behavior when a task K overruns, the behavior of task I could either be normal, so it executes with normal budget, could be safe, it executes with the safe budget, or it could be degraded, so it executes with a budget which is typically smaller than the normal budget value. Okay? So these are the assumptions of this task model. So essentially we say that the execution times should respect certain constraints among each other depending on the specified behavior of the task. And this behavior depends on whether you are overrunning your normal budget, so you need to be executing in a safe mode, and what are the other tasks in the system doing? Have they overrun their budget? Are they executing in their safe mode? So the semantics of this model is also very straightforward. So you start in a normal state, everybody is executing with their normal budget. If some task overruns its normal budget and requires extra resources, you jump to a safe state corresponding to the criticality level of the task that is involved, right? So you jump to a safe state corresponding to this criticality level of the task which overran its budget. And in this safe state, you basically adjust the budgets allocated to the other tasks in some way. And as long as budget overruns occur for other tasks in the system, which have criticality lower than this value, you remain in the safe state. So essentially you have a safe state, one for each criticality level, and it kind of denotes the largest criticality level among all the tasks that have overrun their budget. Okay. So more generally speaking, essentially what happens is that you start in normal state, you transition to some safe state depending on some overrun, budget overrun. You remain in that state as long as no tasks with criticality higher than L have overrun their budget. But if some task with criticality higher than L overruns its budget, you transition to a new safe state and you continue in that new safe state. So eventually the system can transition back to the idle instance whenever your busy period ends and you go back to the normal state. So the budget allocation, I won't go into the details, but essentially it's based on this behavior. So once a task overruns, depending on which task overran, you look at your behavior vector, which tells you what your allocated budget should look like, and you update your budget based on your allocated budget. So you degrade if you need to, otherwise you continue in your normal execution, or potentially sometimes even go to a safe state. Okay. So it kind of is all specified, what are the budgets allocated depending on who is overrun. So we put together this task model and then we decided that we will deploy this task model in an automotive test bed. So this is a test bed we built in-house. So as you can see, there is a simulator, which is a torque simulator connected with the Simulink model of the various subsystems, which then uses some gateways and a CAN network, in-house CAN network, to connect to an ECU where various applications are hosted. So on the ECU, tasks are executing for various applications. We check for budget overruns. If budget overruns occur, we update the budgets based on our task model, and we use a fixed priority scheduling algorithm. So this is essentially a fixed priority mixed criticality scheduling algorithm. So the various functionalities we implemented are lead vehicle detection. So I want to detect a vehicle in front of me. So we use a radar task and a V2V, vehicle to vehicle communication task. So there could be some message exchanges between the vehicle to just indicate the lead vehicle detection. Then based on this information, there is some control. So there is a longitudinal control, so adaptive cruise control, which is basically ensuring that there is a minimum distance maintained between the lead vehicle and yourself. And it uses two different types of controllers, a PID or a on-off controller. An intelligent speed adaptation technique in curves, which is basically slowing down the car and controlling the speed of the car so that the heading error of the car in curves is maintained. So if it goes too fast, then you kind of tend to deviate away from the track. So you try to keep the vehicle in the track as much as possible. And finally, a collision avoidance task, which is essentially an emergency task which runs if the adaptive cruise control is unable to maintain the minimum distance as required. And then for heading error, for lateral control, we use a steer control task, which is basically trying to maintain the vehicle in the center of the track. So all of these applications were collectively implemented on this ECU. And for ACC in particular, we considered different types of degradation. These are all related to performance aspects mainly. So degradation type 1 is you can use two different types of controllers. The PID, which is more robust, versus an on-off control, which is a simple on-off switch to activate or deactivate the ACC. And that one is essentially a kind of a degraded version of the control algorithm. The other type of degradation one could do is no intelligent speed adaptation. So in the curves, you ignore intelligent speed adaptations. You have a slightly higher heading error at the cost of maybe better performance for other applications. So it's a matter of how resources are distributed. The parameters we observed in our experiments are the following. The minimum distance between yourself and the lead vehicle. So this is a safety parameter. Number of collision avoidance activations. How often did you activate your collision avoidance subsystem? The heading error, which is how far away you are from the center of the track. The acceleration error, which is essentially how smooth your control is. How smooth is the ACC performing based on the various aspects. Then we considered various scenarios. The scenarios essentially are which task gets degraded and is it just one task? Are there two tasks that are getting overrun, budget overruns? And then various degradation schemes. So these schemes are essentially existing schemes. So you could just suspend all tasks. You could have fixed degradation for the tasks. You could have some combination of these schemes or the one that we developed and I discussed earlier. For a degradation strategy for the ACC, as I said, there are two types of degradations, no ISA or no switching from PID to on-off. And we basically implemented these two degradations for different types of overrun. So depending on which overrun is occurring. So if the steer task overruns, we degrade ISA. So because the heading, the latitudinal control task already is overrun, you want to reduce the stress on that task. So you overrun, so you kind of degrade ISA. But if the radar or the CA task overruns, which is the collision avoidance task, then you try to degrade the longitudinal performance of the ACC because there are other tasks which are also controlling the longitudinal performance, which need more resources. So it's a kind of context-aware degradation that we do. And as expected, the results are interesting in the sense that if you have this context awareness in your mixed criticality model, you see good performance. So what does that mean? So for instance, if you look at graph A, it shows the minimum distance with the lead vehicle across various schemes. And clearly our scheme kind of outperforms all the others. In fact, if you just do simple suspensions of low criticality tasks, as in the classical model, you are essentially almost always never maintaining the minimum distance. In fact, you are almost always activating the collision avoidance subsystem. The second graph and the third graph are kind of measuring the lateral error and the longitudinal error of the system. So the acceleration RMS and the heading error RMS. And what you see here again is essentially this context awareness. So scenario 2 is where the CA task is overrunning, and scenario 3 is where the steer control task is overrunning. So essentially when the steer control task overruns, we allow for a larger heading error because the heading error control task, the steer task has overrun, it needs more budget. You kind of take a hit in terms of the heading error. But you continue to maintain a low heading error if it is the other scenario, which is the longitudinal task has overrun. So this kind of context awareness where different aspects of the system are affected depending on the overrun context is very interesting in our model. I think it doesn't exist in the existing mixed criticality models. Finally, the last plot shows how many activations of collision avoidance take place. And clearly, based on our approach, you can see that there are 0 activations, whereas other approaches have 1 or more activations of collision avoidance applications. So this brings us to the concluding remarks. Sorry, it's been a bit long, the presentation, but essentially what we have presented is some theoretical results in multiprocessor scheduling, some practical extensions to the mixed criticality model in the uniprocessor setting. What now? Well, if you look at the literature now, there is Still work going on, not maybe as much as 5 years ago. There are some practical extensions that are continuing, dealing with more changes and so on. And there are some theoretical results, for instance, dealing with feasibility conditions for mixed criticality systems. Another question that often comes up to me is, will it ever get used? Will such systems ever get deployed? It's very hard to say, and the only answer I have is patience is the key in safety critical industries. They generally have long incubation periods, and it's never easy to say when these will get ever used or how they will get deployed. With that, I would like to thank you. Sorry, the presentation took a bit longer. I would like to thank you for your time and attention, and these are some of the papers on which the slides are based. And of course, you can go to my website to get more information on all the publications and so on. Thank you so much. Thank you for your time and attention.